Cool. All right. So, hey, everybody. I hope you're doing well. I hope everyone's staying healthy and washing your hands. Um, Today, we are doing Lab 7, which is the rotation curve lab. And actually, this one is going to be our last lab, believe it or not. So, that quiz that you just took is the last quiz you'll ever take in this class. Surprise. Um, That's because normally we have a lab 8, but because that one is pretty hands-on, we're just scrapping it. We're not doing it. So this is the last lab that we're going to do. And let me think. Another administrative thing is some of you have asked about this, and it was already in the works. But originally we were planning on doing an observing night for extra credit, where everyone showed up to the observatory, the planetarium, and we looked through telescopes, and that was your extra credit. Obviously, we can't do that this time. So I have a extra credit assignment that I will be releasing after we're done here today. It's going to be super easy. It's optional because it's extra credit, but I'm sure everyone will do it. It's just a short essay, like half a page even. Um, and all it is I'm asking you to watch a movie because we're in quarantine anyway. So watch a movie where I don't remember the exact outline, but something about the characters going out into space. So, a lot of Marvel movies or Star Wars, Star Trek, something like that. Something sci-fi-y probably. And write a short little half-page essay about what physics in that movie or science is good and what is bad. What did they represent correctly, and what did they just completely mess up with physics? Because a lot of sci-fi movies bend the laws of physics, and so just gonna have you do a little research on that. Shouldn't be too hard. That assignment will count as an extra quiz, so it'll give you an extra 5 points to your total quiz sum. And remember, I'm dropping your lowest quiz grade, so it'll effectively replace a quiz. So probably in your best interest to do it. Any questions about that?
Wait, are you giving us like a list of movies or do we just pick one?
I'm giving you a list of movies that would work, but you can pick one on your own if it meets the specification that they go into space, basically.
What if you do badly on it?
I will be very easy on grading it.
Okay.
Effectively, it's almost a completion grade, unless it's just complete crap. But
Okay.
that being said, don't, you know, hand in crap and expect me to give you 5 points. Actually put in some effort, but
Yeah.
it's supposed to be a fun assignment, so
Mm-hmm.
I
All
won't
right.
be too hard on it. So it's page on a film based in space with what aspects they got. Yes, Zachary. In fact, I think I said it was half a page, so really not that bad. And I'll send out the actual assignment on Sakai after this with more details. Any other questions about that? No? Cool. All right, so today's lab, the whole purpose of this lab is we're trying to get a feel for how the mass of our galaxy is distributed. So is there a bunch of mass at the center of our galaxy? Is it kind of spread out evenly or something in between? And why it's distributed that way? And that's really the big idea here. That's all it is. But there are a lot of nitty gritty details in how you measure that mass. So that's kind of the hard part of this lab. Um, we're not using any afterglow or anything. It's all self-inclusive into WebAssign here. So to start off, I'm going to jump around a little bit in the background section. I'm going to skip all this. And I'm going to start with this part of the background section. And actually, Mm, okay, never mind. Can y'all can see my mouse, right? Because I've been using that a lot.
Yes.
Okay, cool. Thank you. Um, right. So, like I said, we're trying to figure out how the mass is distributed in our galaxy. And if we take a bunch of different parts of our galaxy and measure that, like if there's a chunk of just matter orbiting the center of our galaxy, if we measure the velocity of that chunk for a bunch of different chunks, we can make a plot like this, where basically we're plotting how fast things are moving compared to how far away from the center of the galaxy they are. So if I'm really close to the center of the galaxy, I could be moving really fast, right? That's what this is showing here. Really high velocity at a really close distance to the center. And then as I get further away from the center, my velocity may slow down or stay the same. And hopefully y'all read the background section. The point here is that this graph tells us immediately how things are distributed within that orbit. So if we have an orbit like this, like the Earth orbiting the sun is super massive compared to the size of the Earth, right? So in this case, practically all of the mass is concentrated at the center of this orbit, right? Um, if it was spread out across this orbit, we would see basically the sun filling in all of this space here, but it's not, it's concentrated, right? And using just basic physics, what we can do is get a relationship between a relationship for the mass that is enclosed within that orbit. So Earth is orbiting around the sun, and everything within that orbit, we're calculating the mass of the sum of all that mass. Although in this case, it doesn't matter because it's all at the sun. So we're just calculating the mass of the sun at that point. That interior mass depends on the velocity of the orbiting object and also its distance to the center of that orbit. So in this case, the distance from Earth to the sun. And so that's how, if we rearrange that, we can get velocity as a function of radius, and that's how we can plot this graph here. So in order to understand, the takeaway there is, in order to understand how mass is distributed, we need two things. We need velocity, and we need the distance to the center of the orbit, right? And as you all saw on the quiz, there are two types of rotations that we care about. The first one is this Keplerian rotation curve, and that's for the case like the sun and the Earth here, where almost all of the mass is concentrated at the center of that orbit. And when we plot the velocity versus distance graph, that'll give us something like this dotted blue line here. It'll kind of tail off. So what that's telling us is that when we're really close to the sun, we're going to be orbiting around it really fast, right? But then as we get further and further away from the sun, our orbit is going to be really slow. And that's what it's saying here. Like Mercury, which is really close to the sun, spins around it really fast. It has a very fast year. And then Neptune orbits very slowly because Neptune is further out. The other type of rotation curve is a flat one, which would be B here, the red curve. It's called flat for obvious reasons. And that happens if you calculate the velocity, but the mass that you're looking at is distributed. So if you think about our galaxy, it's a disk and it has all this matter in it. One would think it's pretty distributed, like in this picture here. You have a lot of matter in this disk, and it's somewhat distributed evenly. So you would think that our galaxy would have maybe a bit more of a flat rotation curve. So again, the takeaway here is we're trying to figure out how mass is distributed. And in order to do that, we need velocity and distance. So really, that's the main idea of this lab, but the hard part is getting that velocity. That's what's going to take up the most time on this lab. So now we go all the way back to the beginning. And basically the rest of this background section is building up the knowledge on how we measure that velocity. And we start out with this thing called redshift. Redshift is based on the Doppler shift, which hopefully some of y'all have seen before in physics in like high school maybe. Or it could just be something you've experienced in real life. The common example that people use is an ambulance or a siren that's driving down the street and it's driving towards you. The siren, as it's driving towards you, starts to get higher pitched, or at least it sounds like it's higher pitched, and then it passes you, and as the ambulance is passing you and going further away, the pitch of the siren starts to get lower and lower. That's the Doppler effect. That was with sound waves, but it can also apply to light waves. And that's what these pictures are trying to show you here. So in the middle here, we have a light source. It could be a star, a candle, a flashlight, anything. It's a light source and it's radiating in all directions, right? Remember, light is a wave, so it has a wavelength. That's what these little arrows are trying to show you here. Light is a wave. So the light, as it's traveling to someone in one of these spaceships, it's going to be going up and down like this, right, as a wave. So if everything in this picture is stationary, so this observer on the right here is not moving and the star is not moving, then the wavelength of the light that this star releases is not going to change. So it releases some wavelength, let's say it's 5 meters or something like that. When that light reaches the observer and the observer measures it, they will measure a 5 meter wavelength. That changes once things start moving. So just for notation's sake, we use lambda to denote wavelength, and the observed wavelength, that's what this is telling you, is the wavelength that the observer measures, and then the emitted wavelength is the wavelength of the light when it's leaving the star, right? So again, once we throw in movement into the mix, things start changing. So in this case, the star is now moving to the right towards this observer here. And what happens to the light as it's traveling, it starts getting compressed. So at position 1 here, when it first happens, the star, it releases that light at some wavelength, right? But as that light is traveling to the right, the star is also traveling to the right. And so the wavelength starts getting compressed as you move along. And so the observer here on the right will measure a wavelength that is a lot shorter than it was originally when it first left the star. And the opposite happens if you're watching a star move away from you, right? So that would be the case of the observer on the left. As the star is moving to the right, the light wave is leaving the star, but the star is also moving away from the light wave that it just released. So that light wave is going to get stretched out. And so its wavelength gets longer and longer. And by the time it gets to the observer on the left, the wavelength is a lot longer than it was originally when it left the star. So that's what redshift is, effectively. We call it redshift because most of the time things are moving away from us. So we see that light from stars gets stretched out. The wavelength becomes longer, and that just means that light gets redder. So we call it redshift. Whatever light it was originally, it got shifted to the redder end of the spectrum. Um, and so this is just the math behind it here. So the wavelength that we're observing is equal to the wavelength that was originally released from the star minus the change in wavelength, which makes sense, right? But or it's plus the change in wavelength. It depends on the direction. The change in wavelength, so how much that light gets stretched out, depends on how fast this star is moving in the first place. If it's moving really quickly to the right here, then the light wave that the observer on the right sees, it's going to be compressed a lot compared to if the star was moving to the right slowly, then the light wave may get compressed a little bit, but not much. So that's what this equation is showing you here, is that it's just telling you how much the light wave gets compressed or stretched depending on the velocity, delta V, of the star. Another key point here is that delta V, in this case, that's the velocity of the star, right? It's moving directly to the right towards this spaceship. That's delta V. But it only matters for along our line of sight. So this observer on the right is looking at this star, and the star is moving directly along that line that the observer is looking. But, so that's kind of what this picture is trying to show you here, bit of a change of perspective. You have this observer on the right. The star could be moving directly to the right, directly towards the observer. That's delta V, that's its velocity. But if the star is moving kind of off in some other direction, its redshift or blue shift, whatever the shift is not going to be as strong as if it were moving directly towards the observer or directly away from the observer. What matters is we care about the velocity that is along the line of sight. And that's going to be a big point in this lab. So objects are, of course, not always moving directly toward or away from us. So we have to calculate what velocity they have, what component of their velocity is along our line of sight. Does that make sense? Any questions so far? No? Okay, I think we're good. So that's the idea of how we measure velocity. We base it off of redshift. If we look at an object and we measure some wavelength when that light gets to us, and we know what the wavelength was supposed to be when it was released, then we can figure out how fast that object is moving. So what we need now is to know what wavelength that light was when it was released. And we do that just based on knowing things and science. There are special cases that always release light at a very specific wavelength. In this case, we're going to be using the 21 centimeter emission line. It's called that because it releases light at 21 centimeter wavelengths, so super original. This background section gets into the physics behind it a little bit. That's not super important for this lab. If you want to know more about it, I'd be happy to tell you. But effectively, all you need to know is that you have hydrogen here, and when it's it can be in this unstable state where the proton and the electron of the hydrogen, they effectively act like bar magnets, and when eventually over long periods of time, that instability will cause the electron to flip its bar magnet, and that releases radiation or light, and it releases it. The wavelength of that light is exactly 21 centimeters. And the great thing about this is that this is for cold hydrogen, and there is a lot of cold hydrogen in our galaxy. So I said that it takes a long time for this to happen, right? The lab says it takes almost 11 million years for that electron to flip for one atom of hydrogen. But the sky is lit up with this 21 centimeter emission. So even though the hydrogen is releasing this light very rarely, we still see so much of it because there is so much freaking hydrogen, cold hydrogen, that makes up our galaxy. So it's a great way to trace out all the mass that is in our galaxy. So what we want to do is we're going to be trying to measure the velocity of this hydrogen that is in our galaxy using redshift or Doppler shift. So again, a lot of it matters about line of sight, right? So this picture here is a snapshot of the night sky of our galaxy. We're in our galaxy looking out, and that's a picture of the sky. Here we're looking towards the center of our galaxy. I don't like this picture that much. Doesn't make a whole, it's not very intuitive to me. So that's why we have this picture. So this is a top-down view, and right here, the sun is basically our location in the galaxy, and we are looking towards the center of the galaxy, okay? And remember, we kind of touched on this a little bit I think it was last lab, galactic longitude. Basically, it's just a coordinate system that we use. It's set up so that the 0, 0 of our coordinate system is our location here. So we're at 0, 0. And if we look directly towards the center of the galaxy, that is a longitude of 0 degrees. So what these arrows here are showing you is along this line of sight, we can see a bunch of different chunks of that cold hydrogen, right? And the hydrogen, the whole galaxy is rotating this way, clockwise. So every little chunk that we see along this line of sight is going to be moving in that direction. So its instantaneous velocity is to the right here, or down here, it's to the left, right? Left. So what that means is, remember, these are just clumps of cold hydrogen that are that bar magnet is flipping and releasing light, and that light is exactly 21 centimeters of wavelength. But so it'll release 21 centimeter wavelength light at this point, and then that light will take a long time to travel to us. And by the time it travels to us, it will have stretched out or gotten compressed, redshifted or blue shifted. But for all of these chunks of hydrogen along this line of sight, normally I would ask y'all whether or not it would have a red shift or a blue shift. Kind of a rhetorical question here because I know nobody wants to talk. So the key point here is that all of these chunks along this line of sight, these arrows that we're seeing here, that's their movement. They're moving exactly perpendicular to our line of sight. And remember, redshift depends on what velocity is along our line of sight, parallel to our line of sight. So in this case, for every single chunk of hydrogen that we're looking at along this line of sight, we're not going to see any shift in the wavelength because it is moving exactly perpendicular to the direction we're looking. Does that make sense? Any questions? No? Okay. And so that's what this graph is showing you here is this is the y-axis here is basically brightness, if you will. This is what we measure when the light gets to us. This is brightness versus wavelength. And along this line of sight, remember, there's going to be no shift, red shift or blue shift. There's nothing because it's perpendicular to us. So we're going to see a huge spike in brightness at 21 centimeter wavelength because it hasn't been shifted. I said it was exactly 21 centimeters, but the wavelength is actually closer to 21.10 something. It's down here somewhere. It says it in the lab later, but the line, the actual wavelength of the light when it is first emitted is like 21.101, I think, something like that. So that's what this peak is here. This is that emission that we're seeing, and it hasn't been shifted. If it was shifted, blue shifted or red shifted, remember that light wave getting squished or pulled apart, then this peak would be shifted to the left or to the right. And we see that when we look off in some other direction. So in this case, we are looking not directly towards the center of the galaxy anymore, but off in another direction. So this is going to have some longitude based on our coordinate system. And you can see all the little chunks of cold hydrogen along this line of sight now have different movements. They're not all moving perpendicular to our line of sight. In fact, there's a special one in this case. This guy here, his movement is exactly parallel to the direction we are looking, which means that chunk of hydrogen is going to have the most red shifted emission line. It's probably a lot to remember, like what redshift means and how it plays into all this. So that's why we're recording, so you can go back and watch this. So again, remember redshift, or the stretching of that light wave, depends on the component, the chunk, or I need to stop saying chunk, the component of the velocity that is along our line of sight. I'm going to beat this horse until it's more than dead. So in this case, his velocity is completely along our line of sight, which means that chunk of hydrogen will have the most red shifted light. So when we look along that line of sight now, we're going to have multiple peaks because we're still measuring light from multiple chunks of hydrogen. Some of them are more red shifted than others because some of them have a small component of their velocity that is along our line of sight, whereas there's ones like this one where 100% of their velocity is along our line of sight. So that's why you get this separation of the peaks, because we're basically seeing different chunks of hydrogen along that line of sight. So what this is telling you here is the most red-shifted peak, again, is going to be this one that is completely parallel, right? Most red-shifted for these graphs means the peak that is furthest to the right, because remember, redshift is when that light wave gets stretched, so the wavelength gets longer. So longer wavelength is to the right of the graph. So that's what this peak is here. That is the most red-shifted piece along that line of sight. So we can say, all right, this peak is at a certain wavelength, but I know that when that star, or that hydrogen, sorry, when that star, keep saying star, when that hydrogen released the light, it was at 21.101 wavelength. But now when it gets to us, it's a slightly longer wavelength. And based on that, I can calculate the velocity that that chunk of hydrogen is moving. And remember, to get the to get this plot, we want the velocity of that chunk of hydrogen, and we also want its distance from the center of the galaxy. So to get the center of the galaxy, or center from the center of the galaxy, distance from the center of the galaxy. It's just trig. And you don't have to worry about it too much. I would like for you to understand this equation, but if you want to plug in chug, that's okay too. All this is a zoomed in version here. This is our location. This is the center of the galaxy, and this is the chunk of hydrogen that we're concerned about, the most redshifted one. So this is just trig. The angle from the center of the galaxy to that our line of sight is that longitude that we're looking at. And we know the distance from our location to the center of the galaxy. You measured that in the previous lab to be about 8.1 kiloparsecs. So then the distance from the center of the galaxy of this chunk of hydrogen is given by this equation, where our sun is the distance from the sun to the center of the galaxy. When you're doing this equation, do make sure that your angle, your longitude that you're putting in is in degrees, or else it won't work. So we have the distance of this chunk of hydrogen from the center of the galaxy, and we also figured out what its redshift was based on this peak here, the most redshifted peak, right? And that from that gives us delta V, because remember, we observe it to be this wavelength here, but we know it was supposed to be emitted from that hydrogen at 21.1061. So I was off a bit. Then we can calculate how fast that chunk of hydrogen is moving. But there's one tiny little caveat that you have to add in, and that's that chunk of hydrogen is moving away from us. It's rotating in the galaxy, but also we are rotating in the galaxy as well, just maybe not at the same speed. And so we're basically moving around the galaxy like this. So what we have to do is subtract off our velocity, or actually add it on to whatever velocity we measured, because the velocity that we calculated was just a relative velocity. It's how fast that chunk of hydrogen was moving compared to us, but we are also moving, so we have to add in our movement as well. And that's all we're doing here with this equation. This is the velocity that you actually calculated, and then we add in the velocity of us moving around the galaxy as well. So with that, you have the distance and the velocity of that one chunk of hydrogen. So with all of that, then you get to do it again for a bunch of chunks of hydrogen. So that's what this table is here. Don't let it be too daunting. Once you start getting into the groove of this calculation, it shouldn't be too bad. Again, you can probably do this in an Excel sheet and it won't be too bad. Also, this table walks you through the calculation a bit. So the first thing is we need to put in what wavelength we observe that light when it gets to us. We have a bunch, each row here in this table is a different line of sight along the galaxy. So 0 degrees longitude, the first one here, that's when we're looking exactly at the center of the galaxy. That would be this situation right here. This is looking directly along 0 degrees longitude. And this column here actually has hyperlinks. So if I click on this 0 here, it will bring up one of those graphs for me, the brightness versus wavelength. And I have a peak here, and what you're going to be doing for each one of these is you're going to be measuring the wavelength of the most redshifted peak. Remember, that's the special one. And there's going to be some blending. This data is not perfect, but the key point here is to remember that this is 0 degrees longitude, right? So we expect there to be no redshift whatsoever. And we know that the light that was emitted should be 21.1061. centimeters. So when we look at this, 1061 is about here, which is where that peak is. So that makes sense. In this case, it's kind of hard to read because you may be tempted to say that this here is the most redshifted peak. That is, I'm not exactly sure what that is. That's probably some artifact like line blending. But the point, yeah, so for at least this first one, I would say use the fact that you know it shouldn't be redshifted very much. You probably would take the wavelength to be about here. And you can always like hold up a pen to your computer screen and line it up. That'll make it a bit easier. And it's important to get the correct wavelength here because it actually makes a big difference in the calculation. So let me go through another example here. So this one, for example, this is longitude of 24 degrees. So off at some different line of sight. In this case, remember, I want to look for the most redshifted peak. So that's going to be this one here. So I go to that peak and I figure out what wavelength that is. It's going to be about 21.112, maybe, right? So then I would go back to my table and fill that in as my observed wavelength. And then I know what the emitted wavelength is, 21.1061. I can use my equation to figure out delta V, which is how fast that chunk of hydrogen is moving relative to us. And then this column is when you're calculating how fast the sun is moving around the galaxy. And then you add the two together and you get how fast that chunk of hydrogen is actually moving around the galaxy. And then you can also calculate how far it is from the center of the galaxy based on its longitude. That was the trig part. Any questions so far? This is the biggest part of the lab here is this table. So the calculations are actually not that bad. The hard part is understanding the concepts behind the calculations. That's why I'm talking so long. But the calculations are not too bad. And remember, whenever you're using a calculator or Excel to do these calculations, whenever you have an angle, the longitude that you're plugging in, make sure it's in degrees. And then you're going to be making your own plot using this link here. You're going to be plotting the velocity versus radius that you measured. So these two columns. And you're basically going to be trying to recreate this plot here, velocity versus distance. And you're going to see whether or not it resembles a Keplerian curve or a flat rotation curve, and talk about what that means for how the mass is distributed amongst our galaxy. Then the final part of this lab is just a little bit of an extra step from all of the data you've already taken. So if you remember this section here, when we have something orbiting something else, it depends on the mass that is interior to that orbit, right? And we can calculate that mass using the velocity and the radius of that object that is orbiting. We just found the velocity and radius of a bunch of different chunks of hydrogen moving around our galaxy. So what we can do is we can actually calculate so if I'm looking at this chunk here, then let's say I calculated the velocity and the radius of that chunk. I can now calculate all of the mass that is encompassed within its orbit, if that makes sense. Let me see if I think I can do like a little, I won't try to draw, it'll be bad. But Does that make sense? We have the velocity, we have the radius, so now we can calculate the mass that that orbit is enclosing. And so theoretically, if you do this for a chunk of hydrogen that is close to the center of the galaxy, you calculate that mass, and then you go to a chunk of hydrogen that is further out, a larger radius, and you calculate the mass interior to that orbit, then it should be larger, right? So as you go out in like concentric orbits, you should be encompassing more and more mass, right? Until you get to the edge of the galaxy. And then past that, you won't be adding any more mass. That is what we're doing in this final section here. So for this table, you're using the data that you got previously for all of these different longitudes, and you're using the velocity and the radius that you calculated, and you're taking it one step further and calculating the mass that is enclosed in that orbit. And that's just with that simple equation of v squared r over g. And we give you g here. And then you're actually going to add in 2 more data points. So remember that I said this is for different concentric orbits within our galaxy. But once you get to the edge of our galaxy and you go a further radius out, you don't expect to be adding any more mass because our galaxy has an edge, right? It stopped. And so if you go further out, you're just adding empty space to your calculation. So what we're doing here is we're going to be doing the same thing, but for the LMC and the SMC. If you remember in the last lab, I showed that picture of the Milky Way in the night sky, and there was a blob, kind of like in this picture here, one of these blobs. That was the LMC, which is the Large Magellanic Cloud. And it's another galaxy. It's actually a satellite galaxy. So what that means is it's kind of a tiny galaxy that is orbiting our galaxy, because our galaxy is much larger. And so since it's orbiting us, we can calculate its velocity around us and how far it is, and we can actually calculate the mass enclosed within the orbit of it orbiting our galaxy. But there's a lot of empty space between our galaxy and the LMC, which is orbiting around. There's a lot of empty space, right? So one would think that, remember, you're adding a bunch of different concentric rings, get to the edge of our galaxy, and then you have empty space. You're going further and further, and then eventually you hit the LMC and calculate the mass that is interior to the LMC's orbit. But what we expect is that it shouldn't change because there's all this empty space between the edge of our galaxy and the LMC, right? So if you plot, what we're going to be doing is making a plot, and the plot is going to be mass enclosed on the y-axis and distance from the center of our galaxy on the x-axis. So if you start at the center of our galaxy, let me see if I can, so this is your y-axis, this is your x-axis here. If you start at the center of our galaxy, which is at distance of 0, then you're going to have 0 mass enclosed. But as you start going further and further out, making that concentric ring larger and larger, you're encompassing more and more mass, so you expect it to start increasing until you get to the edge of our galaxy. And then after that, you're not adding any more mass, so you expect it to kind of just stay constant, right? So what you're going to be doing is measuring the enclosed mass of the LMC and the SMC and adding those basically to this table that you did here and making a plot of mass versus radius and seeing what it looks like. And does it look like what you expect it should, or is there something else going on? And I'll give you a spoiler alert. related to the comic that I was showing at the beginning of lab, it's not going to look like what you expect, because what you're hopefully going to see is that it's just going to continue going up and up and up and up forever. So what that tells you is that once you get past the edge of the galaxy and you're still adding concentric rings of orbits that you're going out, there's empty space there, or at least it looks like empty space, but your graph is telling you that as you're going out, you're still adding more mass, which means there's more mass there, but we're just not seeing it. And that's one of the reasons that we know dark matter exists. We can detect it, but we can't see it. So based on physics, we can actually figure out that dark matter is affecting these rotation curves, but it's not visible. And that's kind of the punchline, but few people left anyways, so I'll give you the punchline. Does anybody have any questions? I probably went through that a bit fast.